right, folks. So this is the last set of videos that I'm going to put together for Stat 220 for this semester. And I want to go through just the big concepts that we've talked about and try and pull them all together. Of course, I've chosen to put on my doctoral regalia today because this is the last time that I'm probably going to see you face to face. And if not now, when am I ever going to get to wear this stuff? I don't think I have that many seniors in this class this semester. I think there's just 3 of you, but for everyone else too, congratulations for making it through the year, and for the seniors, congratulations, class of 2020. So I'm gonna start by sharing my iPad screen. Okay, so I just want to do some wrap up of this course, and I'm going to just start by drawing you my favorite picture that I know you've seen many times before. So we have the big thing that is the population, and then we have a smaller version that we call the sample. And the sample was hopefully drawn at random from the population. So we're always trying to make conclusions about the population just based on information from the sample. So we want to draw conclusions about the population based only on information from the sample. And that process is called inference. So that's what we've focused on in basically the last 2/3 of this class, is doing inference. And we're usually doing inference about a population parameter based on a sample statistic. We have lots of notation that goes with this. So some of the parameters that we've studied are a single proportion, p, and the corresponding sample statistic, p hat, a single mean, mu, and the corresponding sample statistic, x bar, p1 minus p2, a difference of proportions, and then p1 hat minus p2 hat, difference of means, mu1 minus mu2, and x bar 1 minus x bar 2. And we've done even more of these parameters and statistics. We had beta 0, that was for a slope, and our sample statistic was B1. We also had lots of means, so like mu1, mu2, mu3, and then we did ANOVA, where we found an F value. And we had many proportions like P1, P2, P3, and in that case, we were doing the chi-squared. So we were doing some chi-squared statistics. So anytime we have a sample, we could compute some number, that would be the sample statistic, and then we're going to use that to make inference about the population parameter. And we have 2 ways to do inference, and those 2 ways are hypothesis tests and confidence intervals. So I just want to go over both of those at least a little bit. So hypothesis testing, we have a set of steps that we have talked about many times before, where the first step is always to state the hypotheses. And then the second step is to compute the test statistic. So the test statistic is based on the sample statistic, but it's not exactly the sample statistic. So it might be a z-score where we have the x bar minus the mu naught, the null value for the mean over the standard error, or it might be an f value, which is the mean squares for the groups over the mean squares for the error, something like that. So our test statistics could be a z, t, f, or a chi-square value, one of those kind of numbers. And then we are going to find a p-value. And we can do this one of 2 ways. We could look in a known distribution. So that would be a distributional approximation, or we could use simulation. So if we're going to use a distributional approximation, we need to check the conditions. But if we're going to use simulation, not as much. So we're going to find our p-value. Then we're going to make a generic conclusion, which is either reject the null hypothesis or fail to reject. Those are our only options. And then step 5 is to interpret the conclusion in context. So I often say that the point of hypothesis testing is to ask, is this number different than 0? And in the sample, it almost always is. You're never going to find a sample statistic that's exactly 0. But you want to know, is that number statistically significantly different than 0? Is the population proportion different than 0? So if we were doing something about a proportion, when we did our test statistic, we would do our observed sample proportion minus our null hypothesized proportion. So maybe, we had a proportion of 0.62 and then our null proportion was 0.5. So we're going to do 0.62 minus 0.5 over the standard error. We're going to find some test statistic. And then we want to know, is that number different than 0? So that's the question that we're asking. And then the p-value is going to allow us to say we have strong evidence to suggest that the number is different than 0, or we don't have evidence to suggest that the number is different than 0. Those are our two choices. And then we need to interpret that conclusion in context to sort of so what in terms of the data. Then our other inferential task that we can do is confidence intervals. And so I usually say the question here is, what are some other reasonable values we could have observed? And for a confidence interval, our generic form is always our point estimate plus or minus a critical value times a standard error. So the point estimate, this is essentially our sample statistic. So it might be p hat or x bar or p1 hat minus p2 hat or x bar 1 minus x bar 2 or b1, something like that. Our critical value, this is going to come from a normal distribution or a t-distribution. Those were the two distributions we used when we were doing confidence intervals in this class. And then the standard error, this is if you're using a distributional approximation and you need the formula. So that's the generic thing that we're doing. And when we interpret a confidence interval, we're going to say something like, I am, whatever, maybe 95% confident that the true population parameter is between the bottom of the interval and the top of the interval. So there's always a correspondence between what you conclude from a confidence interval and what you conclude from a hypothesis test. A lot of the time, what you want to look for in a confidence interval is, does the interval include 0? And that's especially true when you're doing a difference in proportions, a difference in means, or you're doing inference for a slope. It's not as relevant when you're doing inference for a single proportion or a single mean. In those cases, you want to know if the interval contains some null value that you're interested in. But if the interval contains 0, then we can say that we're not very confident about what's going on. Either the mean of the first group is higher, or the mean of the second group is higher. And that means we don't really know which is higher. Maybe there's no difference. If the slope could be negative or positive, that means we could have a positive relationship between the variables or a negative. We don't really know. But if the interval does not contain 0, then we're saying, I'm 95% confident that the slope is between, a little bit negative and a lot negative, right? Either way, we know that it's a negative slope, something like that. And then it also allows us to say what some other reasonable values we could have observed were. So I think that I've mentioned in both these cases that there's two ways that we could do this kind of inference. One is we could use simulation methods. So this would either be randomization or the bootstrap. And the other possibility is we could use a distributional approximation. So the ones we've talked about are the normal distribution, the t-distribution, the F distribution, and the chi-square distribution, and you would need to check conditions. Let's talk about using simulation methods. Simulation methods are a way to get around some of the assumptions and conditions that come with distributional approximations, but they're going to make doing these processes a little bit different. So when you're doing randomization in the bootstrap, you don't always have to compute the test statistic. Sometimes you can just use the sample statistic as it is. So I'm going to show you some examples.